Okay, so here we're looking at a golf ball hit on the moon. We know that it's over level ground, and we know the initial velocity and the launch angle. We don't know anything about the final velocity. Well, we know the x component is the same as the initial x component. We know the delta y is 0 because it's level ground. We don't know the delta x. This is a situation where we can use the range equation because the delta y is 0. So the delta x is vi squared sine 2 theta over g in this case. So we have 1g for the moon and 1g for the Earth. And you could calculate both of them and figure out how much further. But there's a much easier, sort of a conceptually more nifty way. I'm going to make a ratio here. So I'm going to look at delta x on the moon. So that's vi squared. We're going to say that they're both the same vi, like we're trying to compare the same shot to another shot. So the vi's are the same, the thetas are the same, so they don't need subscripts, but the g definitely does need one. And I'm going to divide that equation by the range equation for Earth. The vi and the theta are the same, but the g is different. So what I get here is that delta x moon over delta x Earth is, I can cancel out all of this except for these two denominators, and if I reduce that fraction, I get g Earth over g moon. And I can go a step further. I know that the g moon is 1/6 g Earth. So that goes away, and I can rationalize that even further. So I get the delta x moon over delta x Earth is 6, which means that on the moon it goes 6 times as far as it goes on the Earth. So that's a really easy and neat comparison. It goes 6 times as far. For how much more time was the ball in flight, we want to develop an expression, so it'll be a different expression, but we want to develop one nevertheless. So we know that the delta y is 0. We know what the vi y is, vi sine theta. We know the delta t. We know that the a is negative g, so that's where that negative comes from. Since this is 0, what I can do is divide the whole equation by delta t. So I lose one of the delta t's in each term, and then I can further solve for delta t by moving this over, multiplying by 2 and dividing. So 2 vi sine theta over g will be my delta t. So instead of calculating this number for both the Earth and the moon, I'm going to do a ratio again. So delta t moon, vi and the theta are the same, but the g is different again, over delta t Earth. So that's 2 vi sine theta, those are the same again, over g Earth, and actually it's the same, g Earth over g moon, it's the same ratio, which we discovered was 6. So it goes 6 times as far, and it's in the air for 6 times as long. You could also have said that, well, if you look at the x dimension, it's in CVPM, and the velocity is the same in both cases. So if it went 6 times as far, it must have been up in the well, not up in the air because there's no air on the moon, but it must have been off the ground for 6 times as long. Ratio is really powerful here because I didn't have to resort to the calculator at all here to make this comparison. Anytime you're comparing two things with the same expression, ratio could possibly help you.